Hello, everyone. Thank you for joining today's talk on the idea space. Today, we'll be talking about what the idea space is at a really high level, and then trying to get into a little bit more of the weeds by taking a look at the Idea Space Whitepaper. And so before we start, just wanted to give you a quick kind of table of contents of what today's lecture is going to be about. We'll start with a general introduction, talk about why the idea space is important. Then we'll look into the Sunset Conjecture, which kind of marries the science of objects, things we can measure, and the science of the first person, things we can't measure. Give a little overview of what an idea space is, talk about how it fits with general relativity, talk about how topology can be used to describe an idea space, and then lastly, we'll put everything together through the Cantor set. And so the idea space is important today because it gives a mathematical model for the mind in a way that's congruent with modern physics. And this helps us because when we're able to look at our mind objectively and our thoughts objectively, we can detach from those thoughts, which is really important in the long run for reducing suffering. And so with that framing, let's get into it. So the first thing I want to talk about is the Sunset Conjecture. And the Sunset Conjecture is twofold. The first is that everyone lives at the center of their own observable universe, and at the center of their observable universe lives their idea space. And so I like representing the idea space as a sort of wobble. So just kind of a little squiggle with circles inside, and your observable universe is a giant sphere centered on you, where everything you see is in the past. And why is that? It's because it takes time for light to go from point A to point B, even if it travels at 186,000 miles per second. So for instance, the light you see from the sun right now took 8 minutes to reach you. And then those 8 minutes, you're seeing how the sun was 8 minutes ago. And same thing with the moon. It took 1 minute for light from the moon to reach you. So you're seeing how the moon was 1 minute ago. At the center of the Milky Way galaxies, there's a giant black hole. That took 20,000 light years to reach you, so you're seeing how the center of the galaxy looked like 20,000 years ago. And you can keep extrapolating this thought process farther back and back and back, and you get to this idea, well, what's the edge of your observable universe? Well, if everything you see is in the past, then the edge of your observable universe is the beginning of time itself, right? The hypothetical Big Bang singularity. And the beauty of the Sunset Conjecture is that, again, everyone's perspective of the universe is unique. And the best way to see this is through a little short story. So picture yourself like on the beach, right? It's a beautiful sunset, and the sun's golden rays are pointing right towards you. Happy person. And you look at your friend and you say, man, look at this, it's beautiful. The sun's golden rays are shining right off the water towards me. Your friend says, no, you idiot. The sun's golden rays are pointing right towards me. And they're both right in this case, right? Everyone lives at the center of their own observable universe, and because they live at the center of their own observable universe, everyone's perspective of the universe is different. From a butterfly 5 meters away to a sun that's 8 light minutes away to the edge of your observable universe that's 13.8 billion years old. And so that's kind of the first part of the Sunset Conjecture. Everyone lives at the center of their own observable universe, and at the center of your observable universe lives your idea space. So from here, we can kind of get into the second part of it, is what is your idea space? So again, your idea space is a mathematical model for your mind that is congruent with modern physics. Idea space. And in order to develop a language to talk about this mathematical model, we have to give it some properties to develop a ubiquitous structure. And so we'll talk about the elements of your idea space, and we'll talk about the two main properties of zero measure and accountability. So your idea space has 5 main elements. Thoughts, which include any words, pictures, you name it, songs even. Emotions, anything from pleasant and unpleasant and in between. Sensation, which are the classical 5. Perception, which is your ability to recognize something. So this is chalk. I know this is chalk. And then the null set. And the null set is emptiness. And the null set can be best explained through a little table. So imagine we have a table here that's apples, right? This is apple 1. Apple 2. And this is the color, and this is, does it have a stem? Yes or no. So let's say this is red, this is blank, this, for this one, does it have a stem? No, and then this is blank. So these two here are the empty set. There's nothing there, right? Your brain might try to jump in and be like, oh, this one's yellow. This one does have a stem, but we'll never know. It just is nothing. It's emptiness. And so to summarize, again, your idea space is the amalgamation of your thoughts, emotions, sensations, perceptions, and the empty set, which is represented by the null set symbol. And so with this kind of understanding of kind of what your mind is, we can talk a little bit about the two other properties, which are zero measure and uncountability. Zero measure is a mathematical term, which essentially means that the something looks like nothing. So for example, let's say we have two numbers, A and B here. Something has zero measure if the distance between A and B is less than epsilon for all epsilon greater than 0. So a good way to think about it is just look at this chalk right here. Imagine I split it in half, and then I just made it shorter and shorter and shorter. Eventually, I can make it so small until it has zero measure, at which point it looks like nothing. But the key is that 0 does not equal nothing, right? So again, something that has zero measure will look like nothing, but something that doesn't mean that they're the same thing. And why? It's because you can have, imagine looking at two doors, right? If you look at this door, you know it has, okay, zero measure. And if I look at this door, it looks like nothing. You can't tell them apart. But behind something that has zero measure, you can have uncountable depth, which is something we'll get onto later. But essentially, uncountability defines a size to infinity that is larger than the infinity we use to count. And it is directly correlated to impermanence or an constant state of flux. And so that's a little overview of the idea space. Again, idea space consists of your thoughts, emotions, sensations, perceptions, and the null set. It has zero measure, which means it looks like nothing to everybody else, and is uncountably deep. And where do you find your idea space? At the center of your observable universe. And in order to test kind of all of this, you can hold something in your hand, like this chalk here. Clearly, you can feel it, you can measure it. But if you close your eyes and picture a mental image of this chalk in your head, I see it. Yes, I see it. But then if I asked anybody else in this room to see it, they probably couldn't see the mental image that's in my head. And that just goes to show that your idea space has zero measure and therefore looks like nothing to everybody else. So with this framing, we can talk a little bit more about how the idea space fits in within general relativity as a whole. So we'll start by giving a little overview of what general relativity is, break it down by talking about metrics, which is essentially how you measure distance in space. And then we'll talk about we'll give you some examples of metrics to give you a better definition of a better feel for it. Then we'll flow with what's the idea space metric, and then we'll look at the end a little bit about we can't even read my handwriting anymore. We'll finish. We'll wrap it up with something else. So overview. What's general relativity? General relativity is the study of space-time, and it's all comes down to a famous equation which looks like something like this, which essentially says the curvature of space-time, this is Einstein's field equation, the curvature of space-time is directly correlated to the mass or energy. So this is curvature, and this is mass or energy. And mass and energy are the same by the principle of E equals mc squared, right? And so a good way to think about this is a trampoline. Imagine you have a trampoline. It's going to be long and it extends. And that's space-time. If I put a bowling ball on the trampoline's going to dip. And if I put marbles around the bowling ball, the marbles are going to gravitate around the trampoline. Same thing happens in space-time where the bowling balls are stars and celestial objects or even you. And then the marbles are planets, chairs, you name it. And so you see basically, and this is what Einstein thought of, that gravity is essentially an illusion caused by the curvature of space-time. It's not real. It's a made-up concept that was introduced by Isaac Newton in 1687. And so with this framing, we can get into a little bit more of the weeds as to how general relativity actually works. And so I'm going to erase this. Cool. Okay. So general relativity is all about the study of distances. How do you measure the distance between two things? And in order to do that, it really relies on this concept of a metric space. And like I said, a metric space is essentially how you define the distance between 2 points. And it really has 3 key properties. The first is that the distance between 2 points, x and y, is greater than or equal to 0, and it's only 0 if x and y are the same point. This is the first property of a metric space. The second property of a metric space is the symmetry property. The distance between x and y is the same distance as between y and x. The third is the triangle inequality, which is the distance between x and y plus the distance between y and z is greater than or equal to the distance between x and z. So basically for this one, this is x, this is y, this is z. What you're saying is that the distance plus this plus the distance here is always going to be greater than or equal to here. If you move y all the way down, then it's going to be equal, which fits in that inequality statement. And then these are all for metric spaces, but the idea space is a pseudo-metric space. And so what does this mean? The pseudo-metric space takes this one and kind of flips it on its head, where the distance between x and y can be 0 for all x, y in a space called M. And basically what that means is that the distance between any thought, emotion, sensation, perception is 0 to an outside observer. Of course, for you, you're in there. You can kind of like see what your idea space is. But the whole point of relativity is to say that your experience is completely different than someone else's experience, right? Everyone has their own perspective of the universe, as we saw through the Sunset Conjecture. And so your idea space follows the pseudo-metric. So we can draw it out, where the distance between any 2 points in it, d, is just 0. And because it is 0, it looks like nothing to everybody else. It just vanishes. And so because of this, you need to introduce a new science. In physics, biology, and chemistry, we have the science of objects for things we can measure that live in metric spaces. But we need a new science to study the mind because it has a metric of 0, right? The distance between everything is 0. And this is called the science of the first person. And thankfully, there's been a lot of different techniques over the years that have been developed to study the mind, including mindfulness, Zen, Buddhism. And the goal is on you to build a well-rounded idea space by seeing which one works best, whether it's Stoicism, Transcendental Meditation, you name it. So now that we have the foundations of a metric space, we can kind of see different examples of a metric space. So one that you will definitely be familiar is the Pythagorean theorem, right? What's the difference between 2 points here, right? You do x squared, y squared, and you get c squared, and then you get x squared plus y squared equals c squared. So if you want to find the distance, c equals the square root of x squared plus y squared. Of course, you can take this to 3 dimensions, right? Where I just add z. So c is equal to x squared plus y squared plus z squared, all of that square rooted. This is 3-dimensional. And so that's one example. Another example is the discrete metric, where the distance between any 2 point x and y is just 1. And a good example of this is just an equilateral triangle, 1, 1, 1, right? The distance between all the points is 1 no matter where you are. And then the last one, again, was a pseudometric that we saw here, which describes an idea space. And so when we look at general relativity, you see that general relativity is really inserting metrics into Einstein's field equation. So in mathematical terms, we describe the metrics usually in a way like this, but when you jump over to physics, the metric actually goes by another name, GUV. I don't know why they picked it like that. I don't make the rules. And so what happens is that these values here, I will see in a little bit, are all based on the metric. So once you have a certain metric to describe a certain area, you can plug it into Einstein's field equation and see how the curvature of spacetime will react according to that metric. And so I'm just going to go over a couple of the key metrics that are used in general relativity. But one of the most important aspects of general relativity is that multiple metric spaces can coexist together. So for instance, there's a metric space called the Robertson-Walker metric, which describes the entire observable universe as a whole. And within that metric, you have another metric called the Kerr metric to describe a rotating black hole in space-time. So you can see there's a sort of natural nesting between these metric spaces. And so let's start off with Minkowski space. That's the easiest one. Minkowski metric is a metric for a flat space-time. So while general relativity dictates that space-time as a whole has curvature, locally everything is spatially flat. So essentially what that means is, I'm sure you'll remember seeing this, the distance between 3 points and time is the Pythagorean theorem. X squared plus y squared plus z squared minus ct squared. And the reason you have the ct squared is because you want to get the right units. And so your speed of light is the constant in this case. And so you take the square root of that, and that's how you measure the points between two events in space-time, where an event is just a location in space-time. So if space-time is this blob right here, and this is event A, this is event B. If I want to find the distance between those 2 points in not only space, but in time, let's say this is x, y, z, t naught, x, y, x1, y1, z1, t1. There's a distance between that. So from my distance here to my distance there, not only did I take up space, but that also took up time. And that's how you measure it for us locally. Great for everyday use. The other one is a Robertson-Walker, which I was describing to you a little bit earlier. This one's a little bit much. I'm not going to write it all out because I'll just put it on the video notes, so you'll see it written out much better and you'll actually be able to read it. But essentially, this describes a homogeneous isotropic universe in polar coordinates. So essentially what that means is that in every direction, the universe is expanding in a homogeneous fashion. And so, again, this is what you see here, and we talked about through the Sunset Conjecture. Everything you see is in the past, and at the center of your observable universe lies your idea space. And the last one we'll talk about is the Schwarzschild metric. Schwarzschild. And this guy was interesting. He was like a Russian soldier in World War I, and like wrote a letter to Albert Einstein, be like, hey, I found a solution to your equation, right? And then he died of pneumonia or something shortly thereafter from just like being in the trenches. And so this describes a spherical object in space-time, non-rotating. So think of a star, a black hole. And through this, you can describe different metrics. So these are some of the more common metrics in space-time. You also have the Kerr metric, which describes a rotating black hole. But it follows a similar kind of trajectory. And so the key is like, again, this is metric. And once you have your metric, you need to get the values necessary here in order to solve for Einstein's field equation. And so there's a couple key steps to do that. And there's a lot of good literature on this already, so I'm just going to give an overview of it. But if you want to learn more, I would say to read Sean Carroll's introductory book, Space-Time Geometry, or Stephen Hawking's Large-Scale Structure of Space-Time. Both of those are great reads. First off is the Christoffel symbols. These are essentially the first derivative of the metric. So you have, I'm going to write it down, partial derivative plus partial derivative with v, g rho u plus or minus d rho g u v. And essentially these subscripts and superscripts are essentially represent a matrix or a tensor. And a tensor is just a higher dimensional matrix. So you're maybe used to like your two-dimensional matrix where you have like A, B, C, D. But then imagine that in more dimensions, right, in depth. So this is the derivative of GUV, basically, when we look at it. The next you want to get is the derivative of the Christoffel symbols. And the base derivative of the Christoffel symbols is called the Riemann curvature tensor. And it's the building block of all of general relativity. And it follows a similar pattern where you're just taking this v rho u sigma plus this rho u lambda u sigma minus this rho v lambda rho lambda u sigma. And so again, this is the second derivative. So you can think of it as like the metric is distance, right? X. This is, then the Christoffel symbols are basically like velocity. And then you have the Riemann curvature tensor, which is basically acceleration, right? Think of it like that. And so once you have this, you actually take the trace of the Ricci tensor, which is a mathematical property that you can apply onto matrices. And so you get the Ricci tensor, which looks like this, again, from taking the trace of the Riemann curvature tensor. And then you contract the Ricci curvature tensor in order to get the Ricci scalar. And then what you see is that these are the key building blocks to the general relativity equation here. And essentially, the way that this equation came about was a mix of Albert Einstein and Hilbert. And the whole goal is the action of least principle. So if I toss this up in the air, it's going to go up and down, right? It's not going to go up sideways and fly into a different direction. And essentially, what you're solving for is something called the action. And the action describes the Lagrangian of a function. And the Lagrangian is essentially all of your potential energy, or it's all the kinetic energy minus all the potential energy, right, of a system. And the whole idea is that this whole thing is going to be minimized. And how do you minimize? You take the derivative of it and set it equal to 0. And so if you take the Lagrangian of the curvature of spacetime, you take the Lagrangian of the mass energy, those two are going to be 0. You set them equal to each other. That's how you came up with this equation in the first place. And so again, the whole point of this was to show you that you have a metric, and from getting the metric through taking the derivative twice, taking the trace, and then contracting it, you're able to plug in your value in order to get Einstein's field equation and then see how it describes objects in space-time. So for instance, in the Schwarzschild solution, which is just a spherical non-spinning object in space-time, you see that there's an event horizon, a potential event horizon where anything inside of it, right, light, anything that goes inside of it, all the signals will go back in. So if you have a star, for instance, and this is called the Schwarzschild radius, if the star is on fire, it emits light. Instead of escaping, it's going to go back down. And so through this equation, we're able to predict kind of the path that this light takes and show that the event horizon will form, and that's kind of how we predict black holes in space-time. And so the whole point relating this back to the idea space is, well, what's the metric for the idea space? Well, we said the idea space is a pseudometric. So GUV equals 0. What's the derivative of 0? 0. What's the derivative of 0? Once again, 0. What's the trace of 0? 0. What's the contraction of 0? 0. So you get, at the end of the day, this interesting phenomenon where you have like an idea space, right? If I were to say this is space-time, think of your trampoline. If I put an idea space on space-time, there's not going to be a dip because this has 0 measure on it, right? So an idea space does not directly affect space-time. But if I put an object with measure on it, like a star or something, it's going to cause the space-time to dip. And if it rotates, then space-time is going to rotate kind of like a vortex. And that's kind of what stars are. They're giant spinning orbs through space-time. And so the whole point of this general relativity perspective is to show that the idea space fits within the current regime of general relativity because it is a metric that has of 0. And because it has a metric of 0, it has no direct effect on space and time. And so that's kind of the conclusion for the general relativity part. Now we'll move on to topology, which is a beautiful field in its own right.